Have you ever wanted to turn your Python games into something anyone can play anywhere without needing to install it? So, welcome to Playing Python in the Browser with WebAssembly, and I'm Neeraj Pandey. This is the agenda for the talk, where we're going to talk about what exactly WebAssembly is, what are the challenges in bringing the desktop games to the web. We'll go through some Pygame basics. We'll talk about the PyGBag module, and we'll see how we can convert our traditional Pygame to the web application. So to begin with, what exactly is WebAssembly? If you go with the traditional definition, which you'll find on the internet, it says WebAssembly is a binary instruction format for a stack-based virtual machine designed as a portable target for high-performance web applications. So what we're trying to say is we can build high-performance web applications with WebAssembly, which can allow the use of languages other than JavaScript on the browser, and it can run efficiently in most of the modern web browsers. And we have to talk about the use cases. So computationally intensive tasks, which in the browsers, such as game engines, video editing, complex simulations, all can be done now with the use of WebAssembly. To properly understand what exactly WebAssembly is, let's go through the execution flow of Python first. So you have a starting point where you write your .py files, which is a human readable code written by you as a developer, which then goes to the compilation steps where Python interpreter reads the source code, converts it to a bytecode for most efficiency. This bytecode is for the immediate representation, which is not human readable, but not even the machine code. It's somewhere in between, and it's a platform independent source code. What happens next is it branches out. One section goes to your storage where your PyC files, which are specifically meant for modules, are stored, which speeds up your future loading. And then you have the files which goes to the Python virtual machine. And this is the Python, it's a part of the Python interpreter which reads and executes the bytecode instruction one by one, instruction by instruction into the system. And this is where the program actually runs. Eventually, you have the result of the execution and the program output. This could be a console output, maybe something like a file for writing, a database for changes, and anything. Similarly, if you look into WASM, the WebAssembly, this process is pretty much similar. You have the initial stage where you write your code in different languages, be it Python, C++, Java. Then the compilation step happens where your source code is compiled into WASM bytecode. So WASM code is a pre-compiled into a binary format, and this is very compact and super fast. This is like a very small file structure. This is stored as this bytecode is eventually stored as a WASM module, which is loaded and instantiated in the runtime. It could be a browser or the runtime environment. Then the allocation happens. So memory is allocated for the WASM module to be used by the programs, and the WASM module is then loaded in the runtime for execution. So this linear memory where the allocation happens, this runs as a read and write operation. So every time the program has to do something, it goes to the linear memory, writes something, reads something out of it. Eventually execution happens and the instantiated module is executed to the program and the output is produced. Right, so when we talk about specifically on the browser, if we see that on the left hand side we have the source code, again it could be of any written language, C, C++, Rust, Java, and this is one of the most I would say the flexibility of the WASM, and it's one of the key strengths. Then the compilation happens, the source code is compiled into a WASM bytecode. And this is a very crucial step because it transforms your high level code into a format that's quite efficient for web browsers to parse and execute. Then this WASM bytecode is compiled, and the WASM bytecode is stored into a WASM file, which we discuss. This file mostly contains the binary instruction that will be executed by the WASM runtime. And this runtime differs from different languages to languages. And JavaScript plays a very crucial role in the WASM ecosystem. It's responsible for loading the WASM into the browser environment, and which can eventually be used to interact with the DOM using the traditional web APIs. And the linear memory, which we saw, WASM uses this linear memory model, which is a block of binary data, and this allows the runtime to allocate the memory, and the WASM module can read and write from it directly. One of the most crucial aspects of WebAssembly is it executes inside a sandbox environment. So what does it mean? It's like it ensures that the code directly can't access the host system beyond its allocated resources. So this is like one of the most important things. That another crucial aspect why WebAssembly can be used in the browser, it's the JavaScript interoperability. So WASM doesn't operate in isolation. It has a interoperability with JavaScript, which allows a bidirectional communication between your WASM module and the JavaScript source code. So it can eventually be a part of your DOM, interact with the web APIs, do the DOM manipulation, network requests and everything. And eventually a program output is resulted on the browser. So this is how WebAssembly works, and web is on any program which is written in a not so familiar language for the browser, which is not JavaScript, can eventually interact with the DOM and the web APIs. So what are the benefits of WebAssembly? So the first is a high performance. WebAssembly run at a very near native speed, I would say, if not exactly the native speed. One of the good example could be complex 3D games in the browser without using any plugins, and this could be faster up to like 20 times than JavaScript for certain tasks as well. The second one is a portability. It follows a write one and run everywhere principle, which works across most of the modern web browsers. And third important part is the security, which you can see. As we discussed, it runs in a sandbox environment within the browser, which allows it to only access the resources which have been allocated to it. And it's safer than most of the native plugins you will have in a specific language. So these are mostly the benefits of WebAssembly. And now let's talk about like how we can use WebAssembly with Python, and then we'll see like how we can create games and eventually run them on the browser. So when you're working with WebAssembly with Python, so the step one is a conversion. You write your Python code, it's converted into a WebAssembly module, and yeah, I mean this is like a crucial step for Python to run the browser, which was previously thought of something which is impossible, but now it's possible with the use of WebAssembly. The second step is loading. You have the WASM module which has been created from your Python code, and it's then loaded into the browser. So it's again browser agnostic. I mean, works most on the modern browser, but there might be some of those restrictions. The third step is a JavaScript interaction. So as we know, like JavaScript plays a crucial role for interacting with the DOM. So in order to interact the DOM here, like the Python runtime uses the WASM runtime eventually, and this creates like a bridge between these technologies. The fourth step is the execution. The Python runtime, such as like it's not the traditional runtime, it uses Pyodide here, which is executed within the WASM runtime, and this allows your Python code to run at a near native speed in the browser itself. And overall, this opens up like world of opportunities for you to use. Now we can build like interactive web applications, games, data visualizations, and even educational tools using Python, all running with the power of your single browser. Okay, so few last things before we go to Pyodide. WASM benefits includes near native performance. It can runs at a speed close to your machine code. It runs in a secure sandbox, which means it provides a very safe environment. It has a cross-platform compatibility. It can run on any platform with a compatible browser, which ensures like there's a wide reach happening. Then for the browser environment, a Python interpreter is compiled to WASM runs inside the browsers, and there's a JavaScript interoperability, which allows seamless interaction between the Python and JavaScript. So it eventually bridges the gap. Now our Python can directly access the DOM. And Pyodide, when you talk about these runtime, they have like Python extensive built-in functions are already there as a part of the modules. Libraries like NumPy, Pandas are already a part of this, which can enable you to do complex scientific calculation right in the browser. And it also has compatibility with machine learning libraries, which can open up possibilities to run ML models on the client side itself. That brings us to Pyodide, which enables the Python code to run directly into the browser. Okay, so what is Pyodide? So Pyodide has basically four characteristics. First, it allows your Python code to run directly in the browser without a server. Second, it supports most of the scientific libraries, as we said, NumPy, Pandas, Matplotlib, and more. And it's built by compiling the C Python to WebAssembly. And it also brings the full Python interpreter to the browser environment. And if you have to understand the workflow, that like how things work, you will see that the first step is the interaction, and this is where the process starts when the JavaScript in the browser interacts with Pyodide. And this could be triggered by a user action or a script running on the page. So it can have multiple of those use cases. The second step is the compilation, and the Pyodide on the browser uses the existing Python interpreter that has been compiled to WebAssembly. This allowed your Python code to basically execute it in the browser environment. And if there are some packages being a part of this, then the Python code which you have written loads those packages by the means of Pyodide, and which also has to be compiled to WebAssembly for sure. And then you have the execution part where the user who is writing the Python code uh, is executed by the Pyodide to the WebAssembly compiled using this Python interpreter and the packages all together. And eventually, after the execution, the results are returned to JavaScript, which can then update your web page or perform any kind of access like interacting with the DOM, sending some network requests, and so on. So overall, it provides a something like a foreign function interface like FFI to JavaScript, which allows you to call JavaScript APIs directly from Python. Yeah, so that's pretty much how Pyodide works. And so now we can also like quickly jump into how Pyodide syntax looks like. So if you see on the screen, you have the initialization part. You'll see this. There's a line let Pyodide equals await load Pyodide. This initializes the Pyodide environment asynchronously, and this loads the Python runtime into the browser, setting up the stage for the initial execution. Then there's a simple execution happening, Pyodide run Python, and could be a print statement or any other statement which demonstrates like running a simple Python command. It could be very simple, and this basically executes your code directly into the Pyodide environment. The third one will be package loading. So what we are trying to do here is like we're trying to load the package NumPy into the runtime, and then this again expands the Pyodide capabilities, allowing the use of popular languages into the browser itself. Then you have the JavaScript interaction, which is if you see like pyodide.globals.set JS var, JS value, and this demonstrates how to pass like the JavaScript uh, values to the Python environment, and this enables a seamless data exchange between JavaScript and Python. And then you have the Python definition by the use. The last example shows like when you're defining a Python function and then calling it from JavaScript, it's a very powerful interaction between Python and Pyodide, which basically bridges every single thing. So whatever you normally could have done on a normal, let's say, in Python by just like importing some time, printing some statement, loading a NumPy module will now be directly accessible in the browser using JavaScript. Okay, so this is an example how we can execute the Pyodide operations. So when you see like the init Pyodide function, which is defined on the top, is asynchronous function, and it uses a await load Pyodide to initialize the Pyodide environment. Once this is being initialized, there's a simple Python execution happening, which is python.run Python, and we are passing a print hello with Python statement, hello from Python statement, which initially runs a basic Python print statement, and this output will eventually appear in the browser's console. So if you have to use this information, you have to somehow fetch that information from there. And then you have the Python function execution. So if you look properly, you will see there is a square function over there, which is taking the value of argument 7. So this shows how we can define and use Python functions on the fly along with the initialization. And eventually it's the result handling which is happening. The result of the Python computation is stored in the result variable, and we can then use the console.log in JavaScript to display the results in the browser's console. And all of this thing is making use of the asynchronous nature. So it can use async await, and these are very crucial for handling the asynchronous nature of periodized operations. So we can directly use those JavaScript async await function and do the network call request. Okay. Okay, so now what we're trying to do is we're doing a very small asynchronous setup here, which is using the use numpy function that is being defined as asynchronous, which is very necessary for the periodized operations. And we first load the periodized, then use the periodized load package, which is calling the numpy, which is then loading the numpy library into the periodized environment. Then the periodized run Python async method is run to run a block of Python code, whatever we are running, and which imports the numpy, create the arrays, and these perform these calculations. So yeah, let me quickly go through this piece as well. So here we have a JavaScript function embedded in a script tag within the HTML body. Then we have a periodized setup. The code first loads the periodized numpy package, then executes this Python script which is being running, and this script is then triggered by a button showing how we can do those computational tasks uh, in the browser using Python itself. And this is how you take the input of the code, execute the environment, and take care of the output handling. So this, if you run this index.html file in the browser, you will be able to run those NumPy computation directly in your browser, and you can see the output over there. So now this brings us to the Pygame, which is the popular library for the game development in Python. And this provides modules for handling graphics, sound, and user inputs. It's known for its ideal use for 2D games and interactive applications. And this was released back in the 2000s. And it has been like the go-to choice for beginners and hobbyists and like the Python game development. So to understand Pygame properly, so what is Pygame? I mean, Pygame, as I said, like it's basically a wrapper around the STL library, which stands for the standard directive media or direct media layer. And the STL layer is basically a cross-platform development library designed to provide low language access to the audio, keyboard, let's say joysticks and the hardwares, and it uses OpenGL and Direct3D to do this like a kind of bridging. And Pygame started as a replacement for the previous version, which was called PySTL project, and it's now called the Pygame. And this cross performance nature of STL and Pygames means that now you can write those codes and create those games which are rich in multimedia and graphics and supports all those kinds of platforms. So the programming which will be used is the Python library that provides a game development functionality will be Pygame, and the underlying C library which Pygame uses and is built upon is STL, which handles the low-level operations. And the actual card, the computer hardware or the system you are working on, graphic cards, sound card, and so on, those are the hardwares that the game interacts with. And the Pygame also abstracts the complexities of STL, making it super easy for the Python developers to create games without dealing with low-level intricacies. And STL is also a cross-platform compatible, which means that it allows you to create games which can work on different platforms at the same time. And it's quite flexible. I mean, the architecture will basically allow all the developers to use high-level Python abstracted constructs while still having to able to access those efficient low-level operations which are required to create those and run those games. And yeah, these are the key features, like we can render the graphics, we can do those sound handlings. You can work around with audios. We can take user input. It keeps a loop on checking. It's like when the keys are pressed, when the mouse cursor is happening, and also on. And there's one, the most important thing is the game loop, which provides a framework for the main game loop. It runs as it behaves as the main function in the game, whatever you're creating, and it updates your take care of your handling and the rendering operations. So how does Pygame works behind the scene, or how Pygame works when you're writing a code as a Python developer? The first thing is you import Pygame. So you also need to initialize it. So you initialize after you import the Pygame. This will allow your Pygame to be connected to its abstractions. And basically you're trying to connect to the underlying hardware over there. And there's a function call which uh, is basically called this init call, which is already being a part of the Pygame module. And since these modules are all abstractions of the specific hardware, this initialization step is very much required, that so that you can work with the code on, so that the code can work on Linux, Windows, Mac OS, or any other kind of OS. But now you finally need something to draw upon. So you need a canvas, so that's where your screen comes into play. And now we have a main game loop. So again, it's a loop that keeps updating when the game is state starts and starts redrawing on the screen again and again. And this loop also takes care of the event. So once, unless or until you don't specify any specific event, it'll keep running. It'll never end the loop. So unless maybe let's say a good example is like something happens and the running this thing, the variable is turned to false, and as soon as it happens, it'll break the loop and the output will be put on the screen and the game will end. So that's the main purpose of the game loop. And it also takes care of the event handling. It captures like live events, when the key is pressed, when the mouse clicks are happening, and all this happens in the event queue. And then it renders all the things on the screen. So it's similar to how you render any kind of um, I would say if you have used those turtle tools, or if you have used those graphic vector tools, which takes care of your screen as a 2D Cartesian plane. So it starts from 0, 0 from top left. So similarly, it gives you the ability to draw shapes, images, put some images, add some text on the screen directly using the draw operator. And so now we saw like the very basic initialization setup. Now we'll quickly see like what exactly we can do. So here, what we're trying to do is we are importing a Pygame module and displaying the window. So what you're trying to do is like we're creating the window size, which is going to be the game size and how big the game should look like. And then we're also displaying the images and sounds. So let's say we want some specific image or specific sound onto the platform. We are just like putting up, not the platform, the game, the browser. So we're just like calling it. And here we are trying to handle those event updates and displays. So it checks like what event is happening. Let's say quit function is just like called, or the Pygame quit is called, which is like, hey, just like break the loop and just like close the game. So it takes care of we're taking care of like how we can handle those events and update the displays at the same time. And yeah, so now what we're gonna do is like we quickly gonna create a very small collision-based game where two objects are on the screen and we try to collide one object to the other. When that happens, the trigger will happen and the game will be put up out of the loop and the game will end. So we're setting up the game window. We are telling, hey, this is the size, this is the initial rectangle we want to create. And now what we're trying to do is like we are trying to update the positions of the game objects. We're checking for collisions. We're managing the game logic. We are clearing out the screen so that like everything is like completely fresh. We don't have anything left from the previous section. And we redraw all the elements like the sprites, the backgrounds, the UI, and so on. And this also rendering part also ensures like there's a smooth and visual representation of the game state. Then there is pygame.js pygame.display.flip or pygame.display.update, and this is called to refresh the state with the latest updates or latest changes, whatever is happening. And then we also have like a frame rate control, so that we want to maintain a consistent frame rate on the screen. So we can use the function called pygame.time.clock, which is used to control the speed of the game loop, and it also ensures that the animations are pretty smooth. And this is similar to an event, the game loop which we saw. Like once the quit is like detected, it just like loops out of the game. We can also add movements. We can check for like left and right arrow presses, and we can say like how the rectangle which are acting as a player which are moving. And one thing which you will see is the blit term, which stands for block transfer, and blit is how you basically copy the contents from one surface to the another. And Blit basically does not update the screen. It draws the image in buffer, and you have update and flip functions, which both sends the buffer to the video card, which then displays it on the monitor. And if you have a code which includes like Blit but without update or flip, then it's basically displaying nothing on the screen. Also in Pygame, collision detection is done using the Pygame rectangle objects. So in rectangle objects, we will see like it offers mostly the methods for detecting these collisions between those objects, and even the collisions between a rectangular and a circular object, such as a what do you call this? A paddle and a ball. It can be detected by a collision between two rectangular objects, and this paddle and the bounding rectangles of the box will basically be created by the user itself. And if we run this Python file, you will see maybe we'll see this thing at the end, but it's if you see like closely, this is a video of the same thing. We have one rectangle which is static, and once a second rectangle, we just like try to move it using the keywords, the keys on the keyboard, and once it touches the other rectangle, the quit keyword is triggered, and Pygame stops the loops, and the game gets over. And PyGBag is a tool for packaging these Python games for the web browsers, and it allows your Python games to run without even installing Pygame onto your browsers. And if you have to quickly understand like how PyGBag works, it's in short, it bridges the gap between your Python game environment and web development, and it enables you as a developer to create those apps and run them onto your both the desktop and the web. So that's a beauty. Like it's not like just for creating and running those applications on the browser. You can also run them on the your desktop applications as well. So PyBag uses OnScriptM to compile Python and the Pygame code into WebAssembly, which makes it compatible to run on the latest web browsers. And it also creates a virtual file system in the browser, which efficiently takes care of all the packages which a game needs and the assets for your web delivery of the game. And also works on the asynchronous adaptation. So Python basically implements an asynchronous event loop to make Python's asynchronous code to work in the browser's event-driven environment. So this is mostly like just more information on PyGBag. So let me just like quickly give you an intro. PyGBag here acts as a translator. It converts your Python code into WebAssembly. We have asset packing. So PyGBag functions acts as a packaging service. It packs the game assets, could be images, sounds, music, and everything, and then creates a friendly format for your browsers. Could be any browser. And it also serves as a gift wrapper, which generates HTML and CSS files, and it wraps your translated code and package assets. And the web wrapper, which you just talked, it also includes special instruction which teaches how you can run the game, similar to how the user manual works. And it also sets up your mini environment in the browser, which mimics like how it mimics how the Pygame environment works in your local environment, and then it creates the virtual Python world for the game on the browser itself using WebAssembly. And so this is how like you initialize your Pygame. So the few differences. So we replace the Pygame display.update, which you normally use on your desktop application, to pygame.display.flip. So the reason is the update can be quite slower in the web context, and Flip basically swaps your entire display buffer instantly. So it's often fast and more reliable in the browser environments. You have asynchronous main function. So what is happening here is like it uses an asynchronous define of the main game function, and this is because the web functions, the web browsers we see are like single-threaded event-driven models, and if we don't use those, then the page will become unresponsive and the game will be just like hung behind. And the last thing is the event handling is non-blocking. So for that purpose, we have to yield something like control briefly. And I think we don't have much time left. I think we're already late. So let me quickly say like how we can actually build a Pygame on the browser using PyGBag. So here the game loop is defined as an asynchronous function. It uses the await asyncio loop, like the asyncio.sleep 0 to yield control back to the browser. And we just like start the running of the browser using asyncio.run main, and this starts your game basically. And what will happen if you run that code is like you'll see like a small rectangle on your canvas on the browser itself. So this is a more or less the architecture of how things work. So we're gonna skip this for now, but like if you'll just like go through this, you'll see like there's a Pygame which calls the PyBag, which uses scriptum to compile and so on. And now we're gonna quickly go through the final app which we're creating is a snake schemes. You must have played those snakes on your phone and your desktop application. The first thing is we set up the game environment. It imports the modules. So we importing Pygame, random, async system and all. And this creates the game window, defines the game variables which you're setting up. And if you'll see, we also including the async function, which is very crucial for PyGBag compatibility, enabling the game to run in the browser basically. And this is our main game structure. So this is core functionality of the game which we are creating, and it creates an asynchronous game loop that continuously updates the game state, handles the events, and redraws on the screen. And the await function which you'll see, which calls these async sleep, bracket 0, passing the parameter 0. It's again very essential for web development, which you see like it allows the browser to remain responsive, gives back the control to the browser periodically again and again. And we also have to take care of event handling. So now what we're trying to do is like we want to write a piece of code which manages the user input and snake movement. So what we're trying to do here is we are keeping a track of like how the snake's movement is changing using the user input buttons and all, and we then update the snake position accordingly. This demonstrates how the user interacts and how the PyGBag updates the game object in real time. And this function is specifically for the collisions which you talk about. So what we're trying to say is like we're trying to check for collisions with walls and self, which will end up in closing the loop and ending the game. And we can also, the second block, we'll also try to check if it's going to collide. But instead of ending the game, we want to increase the length of the snake. So this is how to implement like the core game mechanisms, and we are trying to update the game state based on those interactions. This is the drawing functions we have, and these functions are responsible for rendering the game visually. So if you'll see on the canvas, we will see like there are some grids which we're creating here, the food, the snake itself, and so this is how eventually we create those game visual elements, and these perform similar in the desktop and the web environments. And eventually we just like call the asynchronous function which starts the game, and if we run this function in the browser itself, we will see that there is a snake game which is working by going user inputs and just like keep growing, and it keeps growing once we just like go and eats that object, and if we just like touches ourselves or the windows, the game is over. So yeah, I think the session took a little more, but yeah, thank you so much for joining in. I hope we learned a bit about WebAssembly, Python, and Pygame, and PyGBag, and how we can run those Python games in the browser. Thank you, and let me know if you have any questions.